Oh, yeah. All right. So the biggest things we're going to talk about today is we've got to talk about the cells, so their structures and all the jazz that you find inside of the cells, so prokaryotes, eukaryotes, organelle, all that. Endosymbiotic theory. Then we've got to talk about viruses, and we've got to talk about origin of life, so the hypotheses on how life got started on Earth. And then we're going to finish up with immune system, which should be the most recent. Most of you remember immune system, hopefully. Some of you are giving me blank stares. So our very, very first thing it says on here, we're going cells. And we'll start off with the most basic thing, cell theory. All right. So the cell theory, and there's three big things from the cell theory. Thing number one, all things are made of cells. Bye, buddy. Okay, so all living things are made of cells. Next one, the cell is the most basic unit of life. And then finally, any guess where cells come from?
Other cells.
Other cells. It's like you could read it.
Dude, no. I'm gonna act like I'm smart.
Okay.
I'm gonna wow everyone. Don't tell anyone.
You know what's awesome?
Huh.
You just said that right next to the microphone. She goes, I'm gonna act hecka smart because I'm reading the board. I'm gonna wow everyone. Don't tell anyone. I'm like, you're right next to the microphone. All right. So cell theory. All cells are made of cells. So all cells come from cells. All living things are made of cells. So we're made of cells. And the cell is the most basic unit of life. So all living things have to have these cells. So that's our big thing. And so there are different types of cells. There's prokaryotes, there's eukaryotes. Within eukaryotes, we've got plant cells, we've got animal cells. So we've got these different things in there. And so the first thing we're going to talk about, though, is what thing that all cells, regardless of their type, have. So all cells have. All right. What all these cells have, the very, very first thing that all of them are going to have is genetic material. What are the two big ones we talk about? Which are going to be DNA and RNA. So DNA/RNA. And then, number two, every single one of them is going to have a cell membrane. All right. No matter what, whether it's a plant cell, whether it's a bacterial cell, whether it's a eukaryotic cell, whether it's an animal cell, every single one of them is going to have a cell membrane. Yes, plant cells and bacteria cells might have a cell wall, but they still have a cell membrane also. All right. Then we go to number three. They're all going to have cytoplasm. And we're going to go into detail about what all of these do. So if you're like, ooh, Kaya says so, just hold on to your britches. All right, and then finally number four.
Ribosomes.
The ribosomes. The ribohomies. All right, the ribosomes. So all cells, regardless of their type, have them. Your bacterial cells have all of these. Your animal cells have all these. Your plant cells have all these. All these cells are going to have genetic material, cell membrane, cytoplasm, and ribosomes. All right, no matter what. So then we're going to talk about our two specific types of cells we have now. So our first, most basic one, so if we're talking about the origin of life, which one do you think existed first? Prokaryotes or eukaryotes? Prokaryotes, they're the most simple. So prokaryotes right here. What's the biggest thing they do not have?
A nucleus.
No nucleus. They also don't have membrane-bound organelle. Okay, so they don't have membrane-bound organelle, meaning there's no endoplasmic reticulum, there's no Golgi apparatus, there's no mitochondria, there's no lysosome, there's no chloroplast. They have a ribosome. So they have a ribosome, but it says no membrane-bound organelle. Do you remember what composes the ribosome? Proteins and RNA. The ribosome is made of proteins and RNA. It's not made of a lipid bilayer like all these other things are. So that's why it can still have ribosomes, but it's not membrane-bound organelle like these other ones are. So prokaryotes, no nucleus, membrane-bound organelle. Generally, which kind of organisms are prokaryotes? Bacteria. All right. So single-celled bacteria are going to be prokaryotes. Big or small?
Small.
Muy poquito. They're very, very small. Because they're very simple. Think eukaryotes have a lot more stuff in it. If I've got a lot more stuff in me, maybe bigger. That's why you get more grande, because you eat more, so there's more stuff in you. Same thing happens with these organelles. Hi, Debbie.
What's up? Wow.
7th period.
7 periods?
Yeah. Yeah.
Yes.
I know. Thug life.
Test review?
Yep.
No more pepper stuff.
See, Patrick?
We're going to do a test, okay, for you. Right.
I told Patrick I would only give him more if his dad was sitting next to me because he said he wants the entire pepper. And I said only if his dad was sitting in here with us to give consent.
We have to get a fire hose for that.
True. All right. And then finally, bacteria have a cell wall. If it is not round, it's going to have a cell wall. So for instance, and the only reason I'm putting that here, bacteria tend to have a shape like this. All right? Yes, never mind, I'm not going to say that. Okay. Forgot it's recording. Okay.
That's even worse.
Okay.
That's even worse. What are you doing?
No flagellum. Okay. So bacteria has this kind of ovalish shape. If it's not round, it has a cell wall. Bacteria does not have a cell wall, or is not round, so it has a cell wall. Think about a plant cell. Is a plant cell round? Nope. It's not. So they tend to either be square, they tend to be like a hexagon or an octagon in shape. So they're not round, therefore they need a cell wall. Okay? So that's our prokaryotes. Then we get into our next big one, eukaryotes.
Those have a nucleus and organelle.
Eukaryotes have a nucleus. I don't know why I wrote it in all caps. I think I was excited. They have a nucleus, and they also have membrane-bound organelle. And that's what we're going to talk about next. They have a nucleus, and they have membrane-bound organelle. It writes faster. Okay. You guys ready? Ready for our organelles? We gonna go fast. All right. So organelles. I'm gonna go through and I'll tell you general relative structure, and then I'll also tell you what their main function is. So our very, very first one, the biggest, and I'm gonna also put some stuff next to it because some of these organelles fall into other categories, like endomembrane system or endosymbiotic theory. So our very first, when you think of organelles, what do you think is the most, people would argue is the most biggest, most well-known one? Obviously, we talked about that. I was going to say nucleus. But yes, the most well-known one is the mitochondria, because remember, you can't graduate without that mitochondria. You have to know it's the powerhouse of the cell. Nucleus. Okay, so that nucleus, which I'm going to put right here, EMS. EMS is going to stand for endomembrane system. All right? Endomembrane system. Nucleus, what's housed there? Houses DNA. All right, so that's going to be our storage for where our DNA is kept at. And it's part of the endomembrane system, which is going to be this continuous flow of lipid bilayer on there, because on the outside of the nucleus, I have a lipid bilayer, and that's going to continue directly onto the endoplasmic reticulum. Within the nucleus, I have something called a nucleolus. EOLUS. Cool. That thing makes something in there. It's one of the most forgotten about things for some reason. Do you know what's made inside of the nucleolus? Starts with an R.
RNA?
Ribosomes.
done.
It's okay. I'll give you a participation trophy. All right. So nucleolus, and then it's inside of the nucleus, and it makes ribosomes. All right. Now, and I'm just moving outwards. Now I'm going to go to rough endoplasmic reticulum. I'm just going to write ER for smooth. All right. It is also part of EMS. Yup. So it's part of the endomembrane system. Because remember, if I leave through the nucleus and I leave through these tiny little holes called pores, they're going to travel directly down to the endoplasmic reticulum. And it is rough. And what's going to happen, this is going to be like a transport system. And on here, do you remember why it's rough, what it has on there? It has ribosomes. So this is going to be one of the locations for making proteins that are going to be exported out of the cell. Because remember, this endomembrane system is the pathway that we travel from DNA inside the nucleus to RNA out of that nuclear pore, down the endoplasmic reticulum, to the ribosome where it gets translated into a protein. And then that protein is going to travel from the rough endoplasmic reticulum. And so on there, we just went to the ribosomes. At the ribosome, you remember what we said? We turn RNA into what? Protein. That a girl, Bella. Okay. So this is where we go from RNA turns into a protein. All right, so it's the location of protein synthesis, meaning we're making proteins here. It receives RNA, spits off a protein, so that's why it's synthesized there. So traveled out of the nucleus, through that nuclear pore, down the endomembrane system, down the nuclear membrane, into the rough endoplasmic reticulum, to the ribosome where it gets turned into a protein. It's going to go back through some endoplasmic reticulum, and now it's got to go to the next thing. It's going to kind of package it and transport it. Do you know what that next one is? The Golgi. Whoever said that, good on you, mate.
The Golgi.
You could put Golgi apparatus, Golgi body, Golgi. Nope, they're all synonymous. Phenomenon. Okay. So the Golgi apparatus, it's going to transport, modify, and package. This is also made of the endomembrane system. So if it's made of the endomembrane system, it's made of this lipid bilayer on there. All right, so structure-wise, the Golgi apparatus and the endoplasmic reticulum are made of this lipid bilayer that just folds back and forth like this. Oop. All right, so it's made of all these big folds. It's like you took the sour rope, not the ropes, the flat ones. You know what I'm talking about?
Yeah,
and you wind them back and forth. What it really, really looks like, and not many people see it, it's called ribbon candy at Christmas time, and it's like peppermint flavor. Yeah. If you look at Christmas candy, there's like, it looks like a ribbon, and it goes back and forth, back and forth, back and forth, folded back and forth. That's what the Golgi apparatus is going to look like. Do you know what I'm talking about, Maddie? Okay, because I didn't know if that smile meant like he's losing it, or if you actually knew what I was talking about. I knew Hallie did. Okay, so we talked about the nucleus, nucleolus, rough ER, ribosomes, Golgi apparatus. Our next one is I've packaged it up, so now I've got to put it into, the Golgi puts it into a specific package. You know what that package is called? A vesicle. It's a membrane-bound package for transport. And that fact that it's membrane bound is very, 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 very specific because I'm about to send it out of something. I'm about to ship it out of the cell membrane. And if this is made of lipid bilayer and a cell membrane is made of lipid bilayer, it's made of the exact same thing. So it can go straight through the cell membrane with no problem. So this vesicle is this special thing that can help ship stuff out. It's also part of our EMS, our endomembrane system. Yep. And then finally, after the vesicle, that vesicle is going to carry it to cell membrane, which is going to be our final part of our endomembrane system we talk about. It's going to be a lipid bilayer. And it's selectively permeable. Oh, Jimmy Crickets, I forgot one. We got a few more. We got 1, 2, 3, 4, 5, 6 more organelle to talk about. I forgot to put smooth ER in there, but it's not really part of the endomembrane system that we talk about. All right, so vesicle, cell membrane. Cell membrane, lipid bilayer, regulates what can go in and out of the cell, so it's going to help that. Then we're going to talk about our next thing that it's going to kind of act like the garbage disposal for our cell, a lysosome. Lysosome. It's going to break down. Does this lysosome tie in anywhere else with anything else we talk about in this entire unit? It breaks or it has to do with immunity. You know why? The macrophage engulfs it and breaks down those antigens using lysosomes, so it can then take those part of that antigen and present it on the outside, thus becoming an antigen presenting cell. You following along, Simon? No. Okay. So lysosome. Are you really taking notes? Okay.
Just in case I mess up.
A lysosome is going to break down waste. Then we get to some of our fun ones. Centrioles. Centrioles are going to help cell division and structure. All right, it's going to be like part of our cytoskeleton, so it's going to hold that cell, hold stuff in place. It's going to help the cell divide. Cell structure and division. Ooh, que bonita. Any questions? What's your favorite color? Okay, that was loaded. Sorry. Didn't mean to do that. Then we're going to go to, I'm saving my last two favorites. Smooth ER. Smoother. Okay. There's two big things this does. It produces something. Do you remember what it makes? Mm-mm. Mm-mm. Produces lipids. Gotta go, Bella. Okay. It makes lipids, which are fats. And then another thing, do you remember what another big thing the Smooth ER does? We have a lot of them in our liver. It detoxifies. It breaks down toxins. I don't know if I spelled that right.
I'm so dumb. Look the way I spelled it.
I was going to put detoxify. D-E-T-O-X-I-F-Y. How's it
Yeah,
spelled?
but like, I was going to add an S right now.
Oh, yeah. Don't say that out loud. Okay. Okay. Detoxifies. And then finally, we get to our big, beautiful ones at the very, very end. There's two that we left out. The first one, yes, our chloroplast. Not our choroplast. Our chloroplast. Biggest thing, what happens here? Photosynthesis. Meaning this is where food is made for the cell, basically. It's going to take light energy and it's convert it into food. All right. Why it's also pretty significant, it's got a double membrane. It's got ribosomes. It can reproduce independently. And it's got its own DNA. You're probably wondering, why do I care about that? Oh, you wait. Just buckle up. And then finally, last but not least, and our favorite,
El mitochondria.
mitochondria.
Powerhouse
All right.
cell.
Yes. So our powerhouse of the cell. Don't forget that, otherwise Siegel's gonna kick you off the stage.
You're a liar.
No, I promise.
What if he listens to this?
It's okay. He knows. He already does this. He will even verify. He will say, "See, Senor Draz is telling the truth." Yep.
Yeah.
Okay. The mitochondria, biggest process that happens here, cellular respiration. Which makes ATP. This is where ATP is made, in this mitochondria. Don't have a mitochondria, or my mitochondria don't work, I cannot make energy.
Thanks, Mom.
Yep. So we've got this mitochondria, and guess what? This thing also has a double membrane. I know. I'm glad you're excited, freshman. It's got a double membrane. It's the location of ATP production. It's also got own DNA. And it's got own ribosomes. Oh. And it produces on its own, or reproduces on own.
I'm sleepy.
Hey, dude, like, look, we're already through 2/3 of the way through this, and then all we have is this, and then, like, that.
We'll be done before 4. Oh,
Happy dance, happy dance. All right. Any clue why I put these last two together?
they're importante.
Thanks. I could have read that too, but why is that significant?
Because there's some independent
That those things right there that you just told me are the reason why, but why is that significant?
Because they're strong, independent cells that don't need no man.
It's an independent woman. Yep.
I'm gonna write that. It's an independent one. Like, they're independent.
Oh, the endoside.
Oh, you're trying to big old word about that.
Endosymbiotic theory. Well, yep. They once existed as their own cells. Okay, so they once existed as their own cells. Your biggest pieces of evidence that we have for that are going to be double membrane, ribosomes reproduce on their own DNA, double membrane, own DNA, own ribosomes, produce on their own. Those have all the stuff. They have a membrane, they have their own DNA, they have ribosomes, and they also have cytoplasm. Do you remember what those four are the requirements? Cell membrane, genetic material, cytoplasm, and ribosomes. All cells must have those four things. Those have those four things. And so because they do all this stuff, it's believed that at one point in time it existed on its own, and that's called the endosymbiotic theory. And then at some point it was engulfed into another cell, and they started working symbiotically to benefit each other. Okay? Any questions on cells and organelles and any of that jazz? We're going to go into origin of life and viruses now. That'll be a little bit quicker.
Origin of life first.
So here's what you just did about all that organelle stuff. So, yep, we'll go into... Let's go with origin of life first. ¿Por qué me gusta?
I need to take a nap. I'm
Me
tired.
too.
They're abiotic. It's fine. Hey, something.
Okay. So, it's believed that life started on, or Earth was formed about 4.5 billion years ago. And for the first billion years, there wasn't really anything going on here. It was just like, hey, nice rock. Just kind of floating along space, going pretty quick. And then we've got two big hypotheses on how life got started here. Our very first hypothesis, bye, freshman.
Organic soup model.
Organic soup model. And what that organic soup model said, it said these basic molecules such as methane, CH4, ammonia, hydrogen, all of these things existed. All right, so everything was cool. We can make all these things on our own. All these basic molecules like this, under the right conditions, could reform to make amino acids and other monomers. So basic molecules like methane, ammonia, hydrogen, all that could reform to make, I'm going to put AAs, which is amino acids,
No, I thought.
and monomers. What?
They were going to say alcohol.
Don't know. Okay. So they can recombine to make amino acids and other monomers. So now I've got the building blocks of life. So these basic molecules like methane, ammonia, hydrogen, there's some other ones. They can reform and make these amino acids. So now I've got these building blocks. Because if I combine amino acids, I get proteins. If I combine these other things, these other monomers, now I can start building all my big macromolecules. So that's this organic soup model. Under the right conditions, so that's where they did it in there. And then there was an ignition source, and then it condensed, and they calculated them. Then Seabass's favorite one.
Panspermia model.
Okay, panspermia model, meaning a big flaming rock hit us. So we got hit by a meteor. So a meteor hit and brought the monomers. Do you remember what was interesting about the big one we talked about? How many amino acids do we have on Earth that are in us? We have 20. Okay, it had right now, as of right now, they had calculated up to 96 amino acids on that thing. A lot of them we don't even have here. There are more amino acids on that than exist on Earth. So a meteor hit and brought monomer. Evidence was that the one that they found had over 96 amino acids. Right now there's 96. So like the PowerPoint the textbook that I got the information from said it had 84, and then when I looked it up online, between the time that textbook published it and when I looked it up, there was already 12 more. So we're still discovering more. So the meteor had 96 amino acids. We only have 20 in life that we deal with, so it had more than we have here on Earth that we deal with in life here. So that's one of the pieces of evidence. This panspermia model, a meteor hit, brought life here, and that's how we started getting these building blocks, is it came from somewhere else, okay? And so the biggest order of events that we have, so I'm just going to kind of sum up what happened on Earth. So what do you think took place first? Monomers were constructed or polymers were constructed? Monomers came first. All right, so our very first thing was organic monomers. And then our second thing, organic polymers. And then if I put fat or lipids into water, what kind of a shape does it take? Okay, right here, I've got lipids right here. If I were to take this and shake it up, it's kind of hard to see it, but do you know what shape all those little fat globules are taking? They're taking perfect little spheres. So what happened is all of a sudden these little membranes started to form into these spheres. Those are called protobionts. So protobionts formed. And then finally, DNA organisms. That's us, not US. The USA was formed. And that's the origin of life, folks.
That's amazing.
Number 3 says protobionts. That means basically like membranes formed.
And
Simon, how you hanging in there? Vanessa, you following along?
Nope.
Good.
Does it say form?
Forms, yes. Formed. Formed.
Is it biont?
Protobionts. Bionts.
Go over every single. Just a second.
All right. So that's hypothesis of origin of life.
That's cool, dude.
Viruses. Anyone need that list still? Did I go too quick? Okay. So viruses. The biggest thing we got to talk about structure. Within that structure of a virus, do viruses have a cell membrane on the outside?
No, they just take it.
Viruses don't. They have something called a capsid, which is going to be made of proteins.
Don't they act like they do?
Yep. And then they also, so two biggest things viruses have, they have a protein capsid and they also have genetic material.
Nice scam.
Yep. What they can do is some of them can form a viral envelope. Or a viral membrane. And that's when it undergoes that cycle where it breaks out of the host cell. It's going to take part of its cell membrane with it. That way it can scam something out of it and it can make it think, hey, you belong here. And it can infect a host cell even easier.
A host cell.
Yep. So that's its biggest structure. And these viruses that we have, they're called obligate intracellular parasite. Meaning it must have a host cell. And it's specific. For instance, one of the biggest ones we talk about is HIV. And do you remember what kind of cell HIV affects? It affects white blood cells, specifically white helper T cells. Yeah, so it's going to only infect our white blood cells. It's not like our cold, it's going to affect our respiratory tract or anything like that. It's going to purely affect our white blood cells. So that HIV can't reproduce on its own. That's why it's obligate intracellular parasite. It's got to have a host cell, and its host cell is very, very specific. And then once it infects this host cell, now it's going to start taking over, and there's two big cycles. So this virus is going to infect this host cell. It's got to inject its DNA in there, and then it's got to incorporate that DNA into the host cell. And so the first one that we're going to talk about is going to be the lysogenic cycle. We're going to talk about two cycles. You all right? Okay, lysogenic cycle.
It's non-harmful.
Incorporates I'm just going to put GM for genetic material into host. Host replicates it. And it's not harmful. So it can just sit there replicating over and over and over and over and over again. Nothing bad ever happens to the host cell. The host cell probably doesn't even realize it. It's just kind of hijacked it, and now it's having the host cell do all this for it. And then all of a sudden we can get a trigger that says, hey, it's time to break out. I'll let you finish writing while I get more agua.
I'm sleepy. I fall asleep.
We're almost done, folks. All we got is immune system after this. All right, lysogenic, and then do you remember what the other cycle's called? Lytic. Lytic, tomato, cycle. What's going to happen here is viruses assemble.
Dun, 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 dun.
Okay? So, viruses assemble, and multiple viruses break out. Welcome back, Patrick. And this is bad news, bears, because do you remember what happens to the cell when it does this? It dies. So it's called virulent, which means cell dies. Cell dies. Yep, all day, every day. There's none in there, it's water. I have one in my bag. Don't have a heart attack. Okay. You folks ready for immune system?
Ready.
Let me grab my other board.
Can I please have my board, please? Thank you.
All right. Last but not least,
Immune system.
the immune system.
She's not very clear. There she goes.
I like that smiley face. It really pops it off.
I had the smiley face too, but mine's ugly.
Everybody's happy when they got a working immune system. No one likes to be sick. Unless it means you get to miss a test. Okay. So, immune system. We've got 3 lines of defense we're going to talk about. Our first line of defense. If it's our first line of defense, does it care what it's stopping? Zoom in. Okay, if it's our first line of defense, it's called innate. Or non-specific. That's or, not on. Okay, it's innate or non-specific defense. And some examples of this are going to be skin, sweat, mucus, tears, cilia. Inside of our trachea, if you look on a microscopic level, we've got these tiny little hairs. That means if I were a trachea and stuff were to get inside of me, I'd have these tiny little hairs that are brush it up. And so that's why you may be breathing in, and 30 minutes later, all of a sudden, you feel all this stuff up here. It's because all those little hairs are on the inside brushing it up. And that's why a little bit later, you got to hawk a loogie. Because it's those cilia trying to keep that crap out. Yup. So, sweat, tears, skin, mucus, cilia, all this stuff, its ultimate goal, keep it out. Doesn't care what it is, it just says, none shall pass. Keep it out. Okay, skin and sweat, it has a pH of like 4, right? So it's got a pretty acidic pH, meaning stuff can't grow on it. Also, for some of you more than others, it's pretty salty. So stuff can't grow on there. So it's going to help stop that too. Mucus, really sticky. Tears have enzymes. Cilia, they got a mind of their own and they're just going to brush it off. So they're going to brush it out. So that's all first line of defense. It just says, hey, it's not specific. It just says, I don't want you in here. You don't belong in here, so get out. Hi, Natalie. Second line of defense. This second line of defense, also innate. Innate or non-specifico. The very first thing is going to be, if I said you go tell your mother, depending on how much your mother loves you, if you tell her you're not feeling well, some of your mothers will smack you and say, "Ay, mentiroso," and tell you to go to school. But if your mother loves you, what does she do? She fills your head because she's feeling for a fever. Okay? All right? So, we've got a fever because we've got cells in our body that are going to stimulate the increase of temperature. And so the reason why a fever, it's going to try and cook out pathogens. So it tries to cook out pathogens. So that's a second line of defense. Doesn't care what it was, just says something bad is, we've breached our first line of defense. Intruder alert, stuff's inside of me. Let's try and cook it out. Okay? And if that doesn't work, it says, let's flush it out. Inflammation. Okay. In inflammation, we've got these things that are going to cause all sorts of blood to get there, called histamines. Histamines stimulate, meaning it's going to increase. So they're going to stimulate blood flow to area. How was A push?
Not good enough.
Okay. Same thing. Is that Pablo Villaseñor?
Yeah.
Oh, one of you dropped something, I think. Okay. Histamines stimulate blood flow to the area, and they're going to carry non-specific white blood cells. I'm going to put WBCs. So we have some white blood cells that are non-specific, and it just says, "Hey, you don't belong here, so I shall eat you. Get out." Same thing happens in our trachea all the time. So we have macrophages in our trachea. So if stuff gets in our trachea like dust, and maybe we can't get it out, if it's small enough, these little white blood cells are just going to come along and eat it and digest it when it's coupled with which organelle, Hallie? The lysosome. Thank you. So the same thing. So they're going to bring these white blood cells that can help digest it and break it down. Then we get to our third and final line. Third. And our third line of defense is called specific. Okay, so specific immunity, and there's two big types we're going to talk about. Holy crap, you really did take notes. The first one that we're going to talk about, cell-mediated. Immunity. Okay. There. I spelled mediated wrong. It's not mediated, it's mediated. Thank you. Cell-mediated immunity, meaning stuff's got to help out. And so a lot of times what the biggest one is, macrophage. I don't know how to spell this word. Engulfs. FS? There's only one F? All right. Macrophage is going to engulf this foreign particle. We had a name for this foreign particle. Antigens. It's going to engulf an antigen. And then this antigen, or this macrophage, coupled with what Hallie said, that lysosome is going to help break this thing down, and then it's going to present antigen on the outside. Okay, so it's going to take this thing, it's going to break it down, and it's going to Ned Stark this antigen. It's going to present it on the outside. If you don't watch Game of Thrones, you have no clue what I'm talking about. So it's going to present this on the outside of it. And so now, by doing this, it has become an antigen-presenting cell. An APC, antigen-presenting cell. And so now, something can come along and bind with this. A helper T cell. With APC. So a helper T cell is going to come along and bind with this antigen presenting cell. And what that helper T cell can start doing, it can help stimulate the production of B cells and cytotoxic T cells. And so I'll put stimulates.
Just like that fire out of this place?
Yep, that's what I do every day. Room 30, where dreams come to die. Stimulates production of B and cytotoxic. Yep. Cytotoxic T cells. Sorry, kind of small.
Loser.
I know. Everyone's been telling me that my whole life. We're almost done, folks. Okay. Right here, I'm just going to put this right here. Cytotoxic T cells, also known as killer T cells. Cytotoxic T. Do you remember what they do? What kind of bad things? They do kill bad things, but there's a specific... They kill infected body cells. So these things don't destroy antigens. These cytotoxic T cells are going to say, hey, you've been infected. Nice knowing you. Bye-bye. And it's going to kill cells in our body that have already been infected, so those cells don't continue to make more of this. All right? And all of this collectively is known as cell-mediated immunity. I've got to have antigen-presenting cells to help do this. Then I've got one last type of immunity. You remember what that other one's called? Humoral. Okay? Humoral immunity. So in this one, helper T cell didn't bind directly to that antigen. Remember, antigen-presenting cell had to do this. In this one, B cells bind to antigen. Okay? And any number of things can happen to it. It can engulf it. It can become an antigen-presenting cell itself. So a B cell can become an antigen-presenting cell. It can also stimulate production of plasma B cells, which make, do you remember what plasma B cells make? Antibodies. And then we could also have memory. The other B cell was memory B cells. So B cell binds to an antigen, and it can stimulate the production of plasma B cells or memory B cells. If I've got memory B cells, that means now I know how to make these antibodies. And that's the last thing we got to write about is antibodies and immunity. Remember these antibodies? They've all got the same basic shape. They've all got this Y shape like this. What's different about them, though, is at the very end of that Y, there's little protein receptors. that can bind to different antigens. So each antibody is very, very specific to the antigen, kind of like a lock and key. It's got to have the right structure to bind to it. And if I know how to make the antibodies, I can fight it, which leads us to this very last graph that we saw a lot on our thing. I want a bigger line. We had this line right here, where if this was number of antibodies, and this was time, if we drew a line that said, and we said, this right here is first exposure, and this right here is second exposure. What's going on here? Okay. I can make way more antibodies way faster because I remember how to do it. In that time, the very first time, it took me a long time to make my maximum cap of antibodies, which was right here. That's my peak. It took me a long time to get there because I didn't know how to do it. So I had to undergo this whole process of, oh, well, the macrophage is going to engulf it, and then this helper T cell is going to come along, and this helper T cell is going to stimulate the production of other T cells that are cytotoxic, or it's going to stimulate the production of B cells. Those B cells can then form plasma memory cells, which are going to do all this stuff. So it's going to take a long time, or these B cells form plasma cells, which make antibodies. It takes a long time. This time right here, the second time, right there, all of a sudden your body says, hey, I already know how to fight this. So it doesn't take much time at all, and since I already know how to make it, I make way more of them. That was the same reason when you had your B question. You're allergic to the antibodies, not to the actual B itself. And so because you can make way more of them because you remember how to fight it, that's why it's the second time that you get in trouble with it. Okay? Remember, with this immune system, non-specific, do you have to build that up over time? Nope, you're born with it. That's our Maybelline. So you're born with it, and the second something happens, it automatically activates it. Any preguntas? My goal was 4 o'clock. It's 3:51. I'm excited.
Good work.
Dogs on 3. Dogs on 3. 1, 2, 3.
Dogs.
Dogs.
Good team.
Nothing? You guys good? No questions at all? Go on once. Yes, Nenwei. What? I will post a link. I should stop the video. I will post a link to the video on Google Classroom. It's going to get uploaded to YouTube in like 5 minutes.
I think you're cool.